From Dyson swarm to comet apocalypse, it's been 10 years since the discovery of Tabby star, and we finally have a leading contender to explain the strangest known star in the galaxy. Before we get started, a couple of quick announcements. First, we have some new data. Liking and commenting really does help get the episodes shared. So, please do both of those things. And we've also learned that the number one reason that people support us on Patreon isn't actually the perks. It's simply to support the Spacetime community and the work that we do. So for those of you who do support, thank you so much. But don't get me wrong, there are perks and they're good. There's a link in the description if you'd like to join. This really would be a huge help. Next up is our newest merch. Every great space saga starts somewhere. Ours started 13.8 billion years ago. So celebrate one of the most inspiring universes ever created by celebrating the space-time which contains them all. Links to the merch store in the description. We also have a fun announcement about the new TV series, Eon's Life and Death on Pangaea. We'll let you know more at the end of the episode. The galaxy swarms with worlds. Almost every one of the hundreds of billions of stars in the Milky Way boasts a system of multiple planets. Some may be much like the Earth. We know this because the Kepler mission has clocked the minuscule but extremely regular darkening of thousands of stars due to their planets passing in front of them. It's the regularity of these transits that tells us that the shadow is caused by the repeated orbit of a planet. So what do we make of a light curve like this? You've probably seen this before. It's the light curve of KIC 8462854, better known as Tabby star after its discoverer, Tabitha Boyajian. These dips are not due to planets. They're not regular in either repetition or depth. Sometimes up to 20% of the star's light is somehow blackened. For a while, Tabby star became one of astronomy's greatest mysteries. What could possibly be causing these shadows? It inspired explanations ranging from swarms of comets to giant ring systems, and even a brief fascination with the possibility of alien engineering. The galaxy's strangest star then dropped out of the headlines in the decades since, but astronomers continued to study it intensely. Observation after observation, some hypotheses were ruled out and others bolstered. And just last month, a new paper came out that may have found a hidden object in orbit around Tabby star. Not the thing making the shadows, the thing making the shadow makers. The Kepler mission worked so well because planets are extremely predictable and therefore so are the shadows they cast. Planets are very round objects following pretty round orbits. We see tiny but consistent dips in their host star's light exactly once per orbit when they pass in front, for the small fraction of stars whose planetary systems happen to be aligned to allow such a transit from our perspective. The time between dips gives the orbital period, the duration of the dips gives the speed of motion, the depth of the dip and the duration of the dip's onset gives the size of the planet, and together this is enough to pretty thoroughly characterize the world. All of that from its shadows, its very clean and distinctive shadows. But the shadows over Tabby star are far from clean or distinctive, and are certainly not from simple planets. Now, Kepler also worked really well because it's supremely specialized, a camera designed to detect the minuscule dimming of a star out to a few thousand light years with a field of view to monitor over 150,000 stars over its 5-year primary mission. But specialization comes at a cost, and one of the costs was that Kepler's pictures are all black and white. More technically, it had a single filter, and so there was no way to collect spectral or color information. That's okay, because when a planet passes in front of a star, it blocks all light equally and spectral information isn't that useful. A planet is as opaque to blue light as it is to red light. We call such color-independent dimming achromatic or gray. The same should be true of any solid opaque object causing the shadow. That includes a planetary ring system whose icy particles are large enough to block all light they intercept, and certainly most technological structures that we can imagine. But not everything casts a grey shadow. Some absorption is chromatic. The darkening depends on the wavelength of light. For example, Earth's atmosphere blocks short wavelengths of light more easily, blue more easily than green, more easily than red. That scattered blue light gives us our blue daytime sky, and the increased path through the atmosphere during sunset increasingly saps shorter wavelengths, reddening the setting sun. We also see this effect out there in the universe, and the most common type of chromatic absorption is due to tiny particulates, heavy elements blasted out by dying stars that have congealed into tiny grains. In other words, by dust. Obscuration by dust was another leading contender for the shadows over Tabby's star. And here at last we have a real way to test a hypothesis. Planets' giant ring systems, Dyson swarms, should produce grey absorption. Dust should produce chromatic absorption. In 2018, the Boyajian team published new observations of the star in which they showed that the dimming is indeed stronger at shorter wavelengths, just as you'd expect from giant clouds of dust passing in front of the star. Yep, dust. After years of speculation, you'd be forgiven if you were disappointed at the apparent ordinariness of this explanation. But there's a reason we never ever see dust absorption around stars like Tabby's. In fact, astronomers were as perplexed as ever. That's because dust can never just sit there near an active star. The pressure of the stellar radiation will quickly sweep away or destroy the tiny grains. Now, we do see thick dust around some stars. Very young stars are often surrounded by leftover material from their formation, but that dust is quickly blasted away early in the star's life. And very old stars can eject dust in their final phases, but that dust only persists because it's constantly being replenished. Tabby's star is neither young nor old. It's a regular main sequence star, about 40% more massive than the Sun, and is in the prime of its life. The leftover dust of its birth should be long gone, and it isn't producing dust itself. And yet, it's been showing these strange, varying dust shadows for years. So where does the stuff come from? That's now the mystery. The dust must be replenished from somewhere, but from where? And how? Let's return to good old Sol for some inspiration. Our solar system does have a source of new dust, from comets. Way out beyond Neptune are debris fields that stretch a third of the way to the nearest stars. There, frozen chunks of material left over from the Sun's formation drift through the darkness on vast orbits that can take millions of years. But now and then, one of these objects will find its way to the inner solar system. There, it becomes a comet. It begins to melt in the increasing solar radiation and sheds a long tail of water vapor and, guess what? Dust. When it was trapped in ice, that dust had been protected from radiation. But once freed, it forms a streak of material, a cometary tail, that persists only until it's dispersed by solar radiation. Now, this happens only rarely. Objects out in the vast Oort cloud can be gravitationally nudged by passing stars to fall to the inner solar system. Those in the more nearby Kuiper belt are slowly nudged until they have close encounters with gas giants that can smack them further inwards. On their new elliptical orbits, these comets zip through the inner solar system and then spend between decades and gig-years in the outer reaches. It is very rare to find more than one comet in the inner solar system. So, if we want to explain Tabby star's situation, we need a lot more comets than this. Swarms of them. We need some mechanism that's constantly flinging comets at the star. Now, maybe alien spacecraft are peppering the inner planets to soften them up for an invasion, or maybe to seed the barren planets with enough water to begin terraforming. But much more likely is that there's a massive invisible body that's causing gravitational disruption on a much larger scale than we see in our system. This idea of a hidden gravitational disruptor is reasonably convincing, and the idea has been around for a while. However, a dark mass orbiting a distant star is next to impossible to see. So, how do we test this? In 2019, the Transiting Exoplanet Survey satellite TESS watched Tabby's star for 55 days to study the strange irregular dips. It happened to record a single isolated and unusually symmetric dip during that period. At the time, this was thought to be just a slightly odd dust dip. But over the following few years, researchers failed to produce convincing models that would explain this dip in terms of dust. Then, just this year, a team of researchers led by Cristina Maderga-Fevieres put forward a new proposal. Perhaps this dip is not dust, but rather the dust maker. Perhaps it is exactly the type of planetary transit event that Kepler and TESS were built to discover. In this case, the massive body hypothesized to be fleeing comets at Tabby's star. Let's take a closer look at the intriguing shadow. It blocks only about 1% of the star's light and is just over 20 hours long and seems highly symmetric. This is what planetary transits look like. In fact, had Kepler first seen a simple dip like this rather than the crazy ones, researchers would have immediately guessed planet. It was only in the context of the strange dimming that this wasn't immediately flagged as a likely planet. But when we learned that the crazy dimming is probably due to dust, then the existence of a gravitational disruptor to rain comets down on Tabby's star became a prediction, which is why this dip got a second look. The challenge now is that we can't confirm that a planet caused this shadow, at least not yet. Normally, to confirm a planet via the transit method, we need to see 3 transits. 2 full revolutions since the first one. If those 2 transit separations take the same amount of time, then it's a smoking gun for an orbiting planet. Here, we only have 1 transit, so it's only tentatively a planet until 2 more cycles. But not content with waiting potentially years to see if the dip repeats, the team looked backwards in time at old data from Kepler, TESS, and a suite of other monitoring programs for signs of past dips. They found none consistent with the planet, but because of that, they were able to rule out many possible orbits. In fact, they were left with a few orbital periods clustered between 1,000 and 1,300 days as being consistent with no past transit observation. Factoring in the 20-ish day duration of the transit to get the actual planet speed, this gives an orbital period of 3.3 years and an orbital radius of something like 2.5 times Earth's, placing it between Mars and Jupiter in our solar system. From the 1.1% dimming it causes, it should be around 70% larger than Jupiter in size, and that is a huge planet. Earlier, we were talking about comets coming from the Kuiper Belt and the Oort cloud. Now, this star is 43% more massive than the Sun and probably has a commensurately larger Oort cloud, too big to feel the gravity of a planet that close to the star. However, it's also possible that the system has a much tighter ring of icy debris similar to our Kuiper Belt. If this super Jupiter is massive enough, then perhaps it disrupted outer planet formation, leaving a rich field of debris for it to then throw at the inner solar system. But for that, it would want to be very massive, and as it happens, the next stage of this analysis can not only verify the planet's presence, but also measure its mass. After transits, the next most productive way to find planets is the radial velocity method. A planet doesn't actually orbit its star, it orbits its mutual center of mass with the star. And that star also orbits that same mutual center of mass. Because stars are so much more massive than planets, this mutual orbital point is much closer to the star, often actually inside of it. But stars do still move, or at least wobble, in little circles due to their planets. That motion can be detected by watching for the tiny shift in the wavelengths of the star's light due to the Doppler effect. Now, the team used both old and new spectroscopic data to find evidence of that wobble. It's especially difficult with Tabby's star because the star itself is rapidly rotating, which causes additional Doppler smearing of its light. However, the team were able to find a tentative Doppler signature that's consistent with the orbital parameters that they had found for this gravitational disruptor. And the model that best fit the radial velocity analysis gives a ridiculously massive planet, 10 times that of Jupiter. That's encouraging if we want some gravitational beast that's able to disrupt outer orbits. The radial velocity detection is quite tentative. The confidence is 2.3 sigma, which means there's a 1 in 50 chance that the radial velocity signal was a conspiracy of random noise. It doesn't yet qualify as a sure detection, and so more radial velocity data is needed, but we also need more independent approaches, and we're about to get the capability to measure this stellar wobble in a way that was never before possible. Come December this year, we'll be able to measure the literal change in position of stars as they move in tiny circles due to their planets. The Gaia spacecraft was designed to make the most precise position measurements ever achieved. It operated from 2014 until March this year, and we've already learned an insane amount about the positions and motions of Milky Way stars, but perhaps the most ambitious and most difficult measurement it will make is of what we call astrometric wobble of a star due to its planets. And in December, the Gaia team will have completed the highest level of their data processing for the first 5.5 years of the survey, and will release precision astrometry for that period. They expect to discover thousands of exoplanet systems this way. The Tabby star team claims that its astrometric wobble due to this tentative super Jupiter will be visible in this data. If so, the mystery of Tabby's star will be largely put to rest. The star is being eclipsed by evaporating swarms of comets flung inwards by a colossally large planet. And if the planet is not there, well, we keep on thinking and watching and wondering about the strangest star in local spacetime. Hey everyone, before you go, we're excited to tell you that the team over at PBS Eons just finished an amazing new TV show, and it's available now. Eons Life and Death on Pangaea has everything you love about the YouTube show and way more. The series tells the ultimate story of the supercontinent Pangaea during the Permian period, a time of massive geologic upheaval full of incredible creatures, which all culminates in the greatest mass extinction in the planet's history. Check out the link in the description to watch.